How long do you want me to go, since we're running late?
Oh, it's a fire.
No, for 5 o'clock or 5:15, whatever.
5:15, what, I mean,
Okay.
people good with that?
Pushing it.
Let me know if at 6 I'm still talking. So we're going to continue today with the analysis of the data we've simulated over the past couple of days. Well, not actually those 10 events, because we can't do a whole lot of analysis on 10 events. We're also not going to do analysis on millions of events, but it should get you some idea of how to scale this up to a larger number of events. All of this we're doing on small events samples because it is fast enough and it's not going to crash anyone's computer because of memory use or so. Today we're actually not going to spend a whole lot of time in this command line. The only thing we're going to do is start by getting some other Git related files, some Python notebooks that are stored in this Python analysis bootcamp repository. So what we're going to try to, instead of starting up another code space in this repository and everybody having to rebuild it again, we're going to avoid that by just pulling this repository into the one that you already have running. So git clone https://github.com EIC Python -analysis. Really bad at typing today. Bootcamp. So that will get all of the files into this Python analysis bootcamp directory here, which will pop up on the side. And that's all we're going to do on the command line today, because the rest is all going to be Python notebooks. So I think we had about 5 people who were familiar with root. How many people are familiar with Python notebooks? Okay, good. I think that was a smart choice to go with the Python notebooks, apparently. So I'm going to leave this up there until everyone has successfully done this command. Everybody good? Okay. So we're gonna open as a starting point here the getting started Python notebook. So just double click that. We can even hide this terminal because we're not going to need it. And it's actually going to open in code spaces as an executable Python notebook. It's going to look a little bit different than come on. It's going to look a little bit different than a Jupyter interface, but it's going to work essentially exactly the same. Okay. It will work the same, hopefully, soon. I don't know why this isn't loading here. Open. Oh, okay. Okay, so apparently it didn't want to open in this window. We're going to open it. Let's see, close all. Okay, so there we have it. Anyone else having issues opening that file? Or that was just me getting started? The file getting started that's in this Python analysis bootcamp directory that we just get cloned.
I also have trouble.
Okay, so what worked for me was to just right click and then I did open to the side. I don't know why it didn't seem to work when I just double clicked it. Let me see if the second one seems to work just fine if I double click the file. So try right clicking it and do open to the side if it doesn't work by double clicking it.
Open the side, you said?
Yeah, that will just open it in a different tab. But okay, so you got this working. It seems to work here. But then you can actually close all of those tabs. So if you right click on that, then but if you close this one again and see if you can reopen it, you can like just double click it. Okay. Actually, it seemed like it was a couple Hopefully now. It's showing more of the interface. Let's give it a second. Okay, maybe it's because everyone's trying to do this at the same time. Some of you are having this show up, okay?
Can you again show the cloning?
Oh, the command for git clone.
Right.
So let me see. How do I get back to the terminal here? New terminal, no, I don't want a new terminal, but it's probably gonna show up there. Okay, this command. So if you're familiar with Python notebooks, you'll know that the way to navigate through them is, okay, you've copied the line? Okay, good. I'm going to close it. So then you know that you can navigate through this by just doing Shift Enter, which will evaluate cell after cell after cell. And the cells with the gray background are being executed as Python code. So what we're going to do is we're going to use this package called uproot to read in the root files that we created yesterday. In fact, they're not going to be the root files that we created yesterday. They're going to be the root files that the central Epic simulation campaign created yesterday. So they are from yesterday. They're just not the ones that we created here. So this is data, simulated data, hot off the press. So we're going to load this uproot package, Shift Enter, and you should see this connecting to Python kernel. And at some point, it's going to start counting time here. And I don't know why it's saying that there's.
It's install on my end.
Oh, does it need to install extensions?
Yeah.
Yep.
Where do we install? Sometimes this just works fine, and other times it doesn't work fine. Extensions. Jupyter extension, is that it? Which one? Python extension, maybe installed. Uh-oh.
It should.
I swear this worked just fine before.
Yeah, but it should work.
So let's see if this
They are
works.
installed now.
Python extension is now installed.
Also Jupyter is.
Okay. So let's see if this works now. Shift Enter. Come on. I didn't want to do that. Jupyter kernel.
I have the same problem.
You have the same problem. Okay. So let me see if we just reopen this file again. Detecting kernels. I'm confused why this doesn't work. I was using the same code space yesterday.
It's the same.
I have to
problem.
install Jupyter.
You had to install Jupyter too. Okay, so extension Jupyter. It's already installed. So. Okay, then let's see. Then let's go here. Let me just try this out quickly. Create code spaces on main. This should load faster at least.
Reboot the Firefox.
No, don't reboot anything or don't restart anything. So let's just. I'm not actually sure why this doesn't work when it just worked fine. No, that's the name. Okay, let's see, one other thing, oh, this isn't gonna work, there's too many of us here to start this in Binder. We can load this probably in trying to figure out what's gonna be the easiest way to get this working. So let's try this. Yeah, I think. Let's do this. Let's not do that. Let's close this. Let's see if this works. No. Select kernel. Oh, it's still installing it. So yeah, apologies for this. Anyone have any success in the original code space?
So I changed my kernel from the start Python 3.8 to Python 3.10.
So where did you change that?
If you scroll up to the top of the notebook,
Yeah.
and then click on the should be to the right.
Yeah.
Like
So here it doesn't actually show anything.
And Python environments
Python
and
environments.
work Python.
The 3.10, oh, this one? Okay, so let's try that. Actually, that sort of makes sense. So then it should load this, hopefully.
Oh, you're running.
Yeah. Yeah, that's actually, that makes sense that it should be using that 3.10.8. Don't know why it did that automatically the other day. Tutorials are always a little iffy, right? Stuff behaves differently from what you think it should do. So let me see if I restart this.
So whilst being running cells with user bin Python 3 requires the IPy kernel package. Run the following commands to install IPy kernel with the Python environment. So would I have to do it on a local terminal?
Well, all of it is already installed. That's why you shouldn't have to install anything because IPy kernel is installed in there.
Yeah, I think I've now success with this 3.10.8 kernel.
So we can do one other thing, which is a little bit less user friendly. Well, you know, we've kind of passed that. That
Put it on the
threshold.
terminal, let's see what happens.
So there is in this README file, there's also a Jupyter Lab command that you can enter. So that will be something you have to enter in the command line. You can copy and paste it on the terminal, which we've used. I'm gonna just copy this and paste this in the terminal. And if you run that, it should offer to open a different tab in a different browser window. And that's going to give you a regular Jupyter interface. So I'm going to go back to and then this one should work. So if we go back here, so from this file README, at the bottom here, not this README and not any of the other READMEs that might appear there. The last one here, copy these lines and execute them in a terminal, and then click the button that says, yes, open a new browser.
Would it be possible to run Jupyter outside of the code space?
Well, this is running Jupyter inside the code space, but the interface is at least outside of it. So, because I think this is now an issue with the interface.
In what for us, do we do that?
If it worked, then you don't need to do that. It's going to look slightly differently, the interface, but the plots are going to look the same. So and then in interface, you'll see it will pop up with the Python notebooks as well in Jupyter. Okay, let me go around, make sure everyone's set up with some of these ways. Yeah, so at the top of this.
I went in the terminal space. and just-
Oh, I see, yeah, it actually doesn't have that there. So
When I
go, yeah, go
got
to the
the
AIC shell.
recommended me some packages to install. I just did that. That's thankfully.
Oh, which tutorial? I don't know.
So these lines, if they don't appear here, you can also find them on. Wait a second, what's this one doing here? They're also on EIC shell. On the GitHub page. So there are also these lines. Okay, so who has a working way of running Jupyter notebooks now? So we're a couple of people already. And how did you get it to work? You got it,
Just work.
or it's working in code spaces.
Yeah.
Okay, working in code spaces, other people working in, okay. So then, and you have it
in code space.
in code space, okay. So how does it work in code space when it doesn't for others? Is the question now, huh?
Maybe some kind of Windows or Mac thing.
Well, maybe,
Yes.
It's working in code space.
now it's working in code space, okay. So maybe that is what we should try to focus on then. Anyone do anything special or?
Yeah. Probably. Yes, I'm a Leo. Is anybody else? What are your big three? What?
I don't know, I heard you say three and I said, Leo is it three signifies Leos? I mean,
Supposedly in astrology, there's a big three.
yeah.
Like you're rising something or setting. I don't know what they are.
Enable Python.
But I've got places where they're like, everybody give your big three. And I'm like.
Yeah.
So maybe in the interest of moving forward, so those of you who have this working, can you pair up with someone who doesn't have it working? So then we can work through this, even though it doesn't work for me.
No,
But that's at least my.
begin with this Python 3.10a. Try again,
So,
feel this process and try again.
so it doesn't do anything at all. It prints the error. So I kind of need to restart this. Maybe if I change to a different Python environment.
I choose this one, yes, this one.
Sort of.
That one?
Send it
Yeah.
over tonight. I mean, it's not a final, if they're interested in the article, we'll edit it, but if, I mean, it's 4:30. If I send it before 5, they may actually would get it today. Right? And you talked, you just said, I mean, you talked. Yep.
Okay, and this one,
Yep, got it.
this one at least hopefully works. Okay, so I'm going to work in this interface. And I hope for you, you can work, kind of pair up with the people who have it working in either code space or in Jupyter. Let me make the font a little bit larger here. And it's Jupyter Lab, yeah. So back to where I started from. So we're gonna use uproot as an interface to root files. And so in this case, I'm just verifying that uproot loads correctly in Python by printing the version, which doesn't work in code space for me for some reason. But we're using uproot version 4.3.5, which means that it was loaded. So something's working at least. In which you're in code space or in Jupyter?
Jupyter.
So that would happen, let's see. Revert. I see. We close this here, so it's not overwriting each other. So it would say that if you're on the 3.11 Python kernel.
Yeah.
Because that one doesn't, there's no uproot installed for the 3.11 Python version, but there is for the 3.10 version. So that would be, so if you see the error that there's no uproot installed, then you would have to go this one here, to the top here and change to the Python 3.10 version. Okay. And I'm gonna close these files in. So we're gonna load a file that is publicly accessible. All of our simulation outputs get produced in a way that's publicly accessible. And it's located at this server, at this directory under there, and this file name. And you'll see that this is very similar to the files that we created yesterday. It's a Pythia 8 neutral current DIS simulation. It's not 10 on 100 GeV interactions, it's 18 on 275, but it has a minimum Q square of 10 GeV squared. It has beam effects included, it has a crossing angle included, high divergence as well. And then it has it has a few more numbers here. That's what we use to keep track of the large number of files that we simulate. So I'm gonna load those in as variables in Jupyter here, and then I'm going to open this file with uproot, which is abbreviated here as UR. Okay. Overwrite. Just hope it doesn't give me any more grief here. So now events contains all of the events in that event file, and there's, I think if I recall correctly, 576 events for whatever reason. We chop up the simulations in bits that take about the same amount of time to simulate, so the number doesn't really matter. So we can look at what's in that file by looking at the keys, which is similar to trees and branches in root. I mean, it is the trees and branches in root. So this has all of the same kind of collections of clusters and collections of tracks, and there should be MC particles in here somewhere, probably at M, and it probably isn't going to show M because that's a lot of branches and it's cutting it off. But MC particles will be in there. Reconstructed particles, reconstructed charge particles are going to be in there. Everything that is produced by the track reconstruction algorithm. If you wanted to look at just,
I have simple question.
yeah,
Why
sure.
The branches now in the Python we name keys.
Yes.
Why?
Why?
What is the maybe some reason or some connection between the structure of C++ branches and the key structure?
So branches is what the root calls the way things are stored in the root trees. When uproot reads this into Python, it puts it in a Python structure that's called a dictionary.
Yep.
And the dictionaries in Python have keys and values. And so that's why they're called keys here, because they've been ported into this Python structure of a dictionary.
Okay, thank you.
I had to think about that one for a bit too. So yeah, thanks for asking that question. So we got one structure here that's reconstructed charged particles. Those are the charged particles reconstructed by the track reconstruction algorithm. And we're going to use that in this tutorial to reconstruct the x and q square of the DIS events. We're going to use this to reconstruct x and q square in a specific way, only for the electron based on that reconstructed track from the tracking detectors. As I said, you can do this differently, especially for inclusive scattering in DIS. You can calculate X and Q square in any of a number of ways using the electron and using that to calculate X and Q square is one way. It's not always the best way, but it's the easiest one to do a tutorial around. It's also the one that that gives good results for small Q square. And so it's actually going to give us a nice comparison at the end. So that's why we're going to start from these charged particle tracks. So we know the electron has to be in there somewhere. So just to make sure that things are working here with uproot, we're going to make a couple of simple plots. So in this reconstructed charged particles, you'll see that there's different values here, including there's something that is the energy. So that's the energy of the electron. We're scattering 18 on 275. So what do you think the energy of the scattered electron is going to be for a minimum Q square of about 10 GeV squared, approximately? We're scattering 18 GeV electrons on 275 GeV protons, and the Q square is small, so the electron doesn't scatter under a very large angle. 18, yeah, so we expect 18, maybe a little bit of less because we lose a little bit of energy to the protons. So we'll see if that indeed looks like that. So I'll shift enter to read only the reconstructed charged particles into this array. And then I'm going to look at the value of the energies. So we've got one that's 17.7. That's pretty close. But there are other reconstructed particles. There's one that is 5 GeV, one that's 7.7 GeV. There's one this is probably something 0.41. So that's not actually 41, or it might be. There's 8. So there's other particles in there. We can tell this is an array that has 576, that is of dimensions 576 by a variable number, and they're all floating point 32-bit numbers. The varying number indicates that there's a different number of reconstructed charged particles for each event. We have 576 events, but there's a different number of reconstructed charged particles. In some events, we're going to have 1 particle reconstructed, maybe 0, and in others, we might have 10 particles reconstructed. So that will vary. That's common in our field, and so we have to deal with that somehow by making things kind of more regularized, more normalized. So what we do is we take these kind of arrays, which have different entries, sort of they're irregular blocks of data, right? As opposed to square matrices. And what we do is we turn them into one long list of numbers by using this this flatten operation. That's part of a package called awkward to deal with these awkwardly shaped arrays. So we're going to load those packages. These are all common packages developed for high energy physics and particle physics. Yeah.
When I try to
A value.
charged particles, then I
Get on number 2.
Let's see, can you scroll up a little bit? And this is after loading, after opening the file, did it print out the keys correctly? Yeah, that correctly. Okay, that looks good, yeah. And then ran this one too, yeah. Yeah. Yeah, scroll down a little bit more. You got the same array?
I don't know, is it?
Yeah, mine did.
IO. So sometimes what happens is that the Python notebook sometimes closes the file. So in your case, it says IO on closed file. So it might be that you have to go, that's not a mouse, that you have to go up and reopen that file up at the start of the file when we did this line. So it may be that you have to reopen it. So there's different reasons why sometimes this happens. Let's see. Scroll back down here. So yeah, if you don't get any values here, it might be that the file got closed, and if it gives you an error, usually it will indicate something like file IO error, so. Okay. So now that we have these values, we can flatten this array. And you'll see now we have a one-dimensional array that has 4,797 entries. So there's 4,797. Yeah, no problem.
Same.
No need to apologize.
here.
Hmm.
We did the same.
I don't know.
Something.
Maybe I opened.
So try to, this is in, okay, yeah, this is here. One of these is restart this one probably, right?
Yeah, this is fine. Yes, here.
So let's see if after you restart, whether you can run everything from the start. Yeah, let's try that. And now another one. Okay, so try running through it. So sometimes you have to restart the notebook.
The corner, like in mathematics.
When I tried this, I was getting the same.
So try to restart as well, next to it. Yeah, restart and then just start from the top.
Okay, now
again.
it's okay.
Oh, okay.
Yeah.
So now that we have this flattened list, and it clearly indicates there's about maybe slightly less than 10 tracks, charge tracks per event, right? So now we can turn it into a little plot, a histogram, which I've done here. This is using matplotlib, a very common package in Python for making all kinds of plots. So I'm going to make a histogram of this flattened reconstructed charged particles energy between 0 and 50 GeV, and I'm going to have 50 bins. So the first bin 0 to 1, second bin 1 to 2, and so on. I'm going to make sure that my plots are labeled on the X and Y axis, otherwise I don't have any right to complain about that with my students. I'm going to put this in a log scale in the Y axis, so you actually see the kind of structure in here. And so you can see we have lots of particles that are at low momentum, these charged particles. But most of them are actually in sort of this range below 10 GeV. We've got a peak here at, what value is that? 18 GeV. So those are probably going to be our charged electrons, but we can't tell that from the momentum itself. We would need identification. And then we have some particles that are actually very high energy. So those are going to be hadronic particles that are, that were really caused by quarks that got knocked out of the proton. So this was just to get us started. How do we open files? How do we load them? How do we make a little plot with them? So now we're actually going to do go into the real analysis. So the first thing we're going to do is accessing truth information. So I'm going to open this accessing truth information file. And so it's going to be, all of these notebooks are going to look exactly the same at the top. They're going to load the uproot package. Okay. So ignore the fact that it still says Athena here. I thought I caught all of the old naming, old detector collaboration names, but so we're gonna just go through this, and you don't necessarily have to click every time on an executable cell and press Shift Enter. You can just keep pressing Shift Enter, and it will just go through it one by one, even through the text lines. So this is just opening that exact same file that we just looked at. But now we're going to look at this MC particles branch. We've already looked at this MC particles branch yesterday, and this is the truth information, right? This is the original event. So in our HepMC input file that Pythia 8 generated, this would have produced, the pions, the electron angles, the direction of the electron. So this is what we know is the true momentum for the generated particle. And so one of the things, if you're you're interested in studying the tracking detectors, is you would look at how does this momentum that we've reconstructed, how does that compare to the true momentum of that particular particle? So this would be a way to access that. Now, what we're going to do here is, what we're going to do here, we're going to look at the momentum at the particle data group code. Okay, just have to peek ahead a little bit here. So that's going to be this PDG field that will give us the particle data group code. So we'll be able to use that to look at whether something is particle type 11 for electrons, or whether it's 211 for pions, or minus 211 for negative pions. So we're going to use that. And we're going to store this particle data group code in a list, in an array. We're going to store the generator status in an array. That's going to allow us to separate between particles that were generated by FMC, by Pythia, and particles that were generated as secondaries in the detector. And then we're going to store the momentum X, Y, and Z vector, or the components of the X, Y, and Z, the X, Y, and Z components of the momentum vector. So this should now give us these 1, 2, 3, 4, 5 arrays. By the way, I think there's a little debug. It doesn't seem like it's working today. This might work for some of you, but sometimes it shows. I guess if we are not dealing with technical issues, then it would show those arrays, and you can actually look at the values that are in them. Since it doesn't show it here, we're just going to print the particle data group codes for one event. This is the 100th event. Actually, it's the 101st event because it's starting at 0. And so in event 100, there's 50 particles in the truth record. Again, those are particles that are generated by Pythia 8 and that are used as starting point for the simulation, or particles that are also then generated inside the simulation, inside the tracking region. And you see there's a proton here. There's a particle number 2. What's the particle data group code 2 stand for? It's a trick question. There's no particle data group code 2. Well, there is one. It stands for a diquark. But it's not, of course, a particle that you're ever going to see in real life, because diquarks don't ever end up in the final state. 2103, anyone an idea what 2103 can be?
Diquark.
What is it?
A diquark.
Is it a diquark?
Yeah.
Is 2103 a diquark? What is 2 then? No, 2 is it?
2 is just an up quark.
2 is just an up quark. Ah, right.
the-
Yes, of
I have
course.
the
Yeah.
table pulled up.
So this is the diquark. Right. 11, the electron, 22 are photons. Now again, diquarks, quarks, up quarks, they're not necessarily particles that have that have been thrown into the detector, right? So that's what this generator status code is for. That allows us to compare with this. So this proton has a generator status 4. These arrays are sort of progressing in parallel, right? So the 4 corresponds with 22, 12, 61 with this 2, 63 with this 1, 4 with the 11. Now the generator status code 4 in the FMC standard means that these are incoming beam particles. So this particle is going to be the incoming proton. This one will be the incoming electron. If we look at the energy, they should have 275 and 18 GeV respectively. Only particles with status 1 are final state particles for the hard scattering interaction that Pythia simulates. So those are the ones that actually went into the detector. These are stable particles that go into the detector. So pions and stable on the distance scales of a detector. So K long particles would be considered stable in these contexts, for example. So those are the stable particles that we're going to have to look for. And so our scattered electron is going to have a generator status 1. Otherwise, we're going to look at internal edges of the scattering graph that are electrons, or we're going to look at the incoming electrons. So we're going to often use this generator status equal to 1 condition. So that's sort of what's in these events. Now the other thing we stored was the momentum in the X, Y, and Z direction, incoming momentum in the X, Y, and Z direction. What we're going to do with that is just do some math on those entire arrays. So this is an array, and I'm going to square every element in that array and add it with the corresponding element in the Y component and the corresponding element in the Z component. That gives us P, which is going to be an array that is going to have the same size as the original arrays, but it's going to contain the total momentum. So for event 100, this is our total momentum, 275. That's indeed this incoming beam proton. It doesn't show the electron here, but it would have shown it here. This is actually the momentum of the magnitude of the momentum of that up quark. This is the magnitude of the momentum of the diquark. Because of momentum conservation, those are both inside proton, so they should add up to 275 approximately. So that's what you see there. And then you see the momenta of these other particles, photons, that were generated in the detector. Okay, so we got a little bit more information now than just the magnitude of just the energy, which we looked at before. We've actually got the momentum, which is usually a better quantity to look at than energy, because it's, something has an energy of 1.2 GeV. Does that mean that it's a proton with 400 MeV kinetic energy or momentum, or is it an electron with a very large momentum? So momentum is generally what we want to use. And the other thing we can use is we can use the momentum to figure out the scattering angle. So here we're going to take the X and Y components, sum them in quadrature to get the total transverse momentum, and compare them with the Z component to get the scattering angle theta. And then we're going to look only at the scattering angle theta for events or for tracks that did go, for particles that did go into the detector, those generator status 1. So again, we've got our 576 events, a varying number of tracks that went into the detector. And we can plot this, and that's how it looks like. So similar to our energy histogram, we can look at this angular scattering histogram. Now, I'm using a little trick here, which anyone who's not used to looking at the EPIC detector or EIC detectors might think is really weird, because I'm not plotting the scattering angle, I'm plotting the negative scattering angle. So these are events that all have a positive scattering angle, right? Scattering angle is by definition between 0 and pi. But I'm plotting it in the negative direction because all of the figures you'll ever see of the EPIC detector have the scattered electrons that are scattering under large scattering angles. And this is going to be our negative end cap. This is going to be our positive end cap. So the particles with a scattering angle that's close to 0 are going to be in the part of the detector that's usually drawn on this side, and the part of the tracks that have a scattering angle of nearly pi are going to be in the part of the detector that's drawn on that side. So this is sort of a way of then making sure that when you plot this histogram, this kind of corresponds with how we think of the detector. The stuff on that side goes into the negative end cap, stuff on that side goes into the positive end cap, and the stuff in the middle goes into the barrel. So that's what those, that's where the particles end up. Now, I'm going to ask you, or you were going to ask me something.
Yeah, just to make sure I understand. So this is, we're in the negative. So if we were not to be plotting leptons, it would be positive. That's what you're wanting to show. based off of how the detector is set up, right?
So let me see if I can quickly pull up a picture of the EPIC EIC detector. Hopefully Google is going to come back with something useful here. Okay, so let's see. Bigger and even bigger. So this is our detector, right? So those events that were on that side of the plot are going to go at small angles in this direction.
Exactly, yeah.
The ones that are on that side of the plot are going to go at small angles in this direction.
Yes.
So that's why, because there's a way in which things are drawn in the experiments, and it's always electrons come from this direction, protons come from this direction, and the scattering angle is defined by how much the parts that come out of the proton are scattering with respect to the original proton direction. So that's why it sometimes makes sense to plot this in the negative direction. Okay. So we've got a little exercise here now. So we have more information here than just the momentum, right? We have also the particle code. So I'm going to ask you as an exercise to plot a stacked histogram that has one particle type in one color. Hopefully these are all going to turn out to be electrons. Other particle types in different colors, so that you can see where different particles end up in the detector. So you can use some of the ideas of how to make selections in these values of theta. You might need to Google something about how to make stacked histograms in Matplotlib, but you should find a link to that relatively easily. Adam, I'm going to hide the solution here. I'm going to let you all work on that for about 5 minutes or so. Yeah, well, I've done this one with Google Colab. It takes a little bit longer because it doesn't have Uproot installed by the way. So everyone has to go through installing that. What else? Possible thing.
G number. I was actually angry. So like I know that.
Yeah, they're charged particle.
11, right? I never even looked. It's like,
Yeah,
I put 21 on the check.
Yeah.
So how do we get like photons?
Protons. So this is something that we're actively working on right now, and there's code that's just not in the main development, it's not in the main branch. So that's something that is not in this. Will be in literally the next.
Yep, contribution in the next campaign. Okay. Gotcha.
It was actually in like the stuff we were doing yesterday.
Yeah.
But that's not part of the main
Right.
thing. So,
You're just thinking by hand.
yeah, exactly.
So-
Yeah. Oh, you're looking at solution. So of course you can look at the solution. But one of the things that is useful is to think about, how would you approach this, right? What is it that, do you have an idea of how to do this?
I mean, I know, and like if I had words, I would do it a different way, but
Right,
it's just syntax.
that's true, it's syntax.
It's Uproot.
I see. Concern if this is just from macro, then
So the reason why we're using Python here is because,
simple.
well, it's not necessarily simpler, it's because more people know Python.
Right. Yeah.
But yeah, you're of course welcome to do this in root. I mean, the same thing is true. You can load the same files from the same URL.
And that's saying ones where like, saying that the syntax and stuff.
Mhm.
So it looks like you're making an array of.
Is there a standard
amongst the Epic collaboration right now?
No, so we're trying not to make a standard, not to impose anything. Like, if you wanted to analyze this in Excel, be my guest. We don't wanna, that's part of the reason why we picked the data model in the way that we did, is to allow that kind of freedom. Because storing things in certain ways that are more difficult to access, if it becomes too structured, then, for example, you can't feed it into machine learning models as easily. Or you can only feed it into machine learning models that understand that highly structured data. And that's why we're trying to keep things as simple as possible, so you can use root, you can use Python, you can use whatever you want.
Thank you.
So I'm just gonna go through this possible solution that you could use here, and to some extent you have to experiment with that a little bit. So one thing that might be useful is to think, which particles are there going to be in a detector? It's probably going to be, I think, mainly, well, we saw already some photons, so PDG code 22 is going to be in there, and then there's certainly going to be electrons, potentially some positrons too, and then there's going to be pions. There might be kaons in there too, so we'd have to look up the particle data group code for kaons, which I don't know, what is it, like 213 or so, or it must be a 3 in there somewhere.
Chaos are 311-ish.
311,
Around there, yeah.
So what I've done here is I've split it up into electrons, photons, and then either positive or negative pions. And then I use this stacked is equal to true to let matplotlib make a nice stacked histogram of this. And so you can see, I'm colorblind. I need to figure this out. Okay. Yeah, so you can see that most of the pions are sort of in the direction, in the forward direction. So most of the pions are going to end up over here. Most of the electrons are indeed ending up over here, consistent with our small q square. Not a lot of large angle scattering for the electrons. So the electrons that come in here are going to end up in this region, and then we've got photons that are also mostly ending up on the sort of small scattering angle side here. So that gives us some idea of how to do this this analysis, and we get some idea about where things end up for particular data sets. So that was truth information. So now we're going to go to determining x and q squared in these events. And so we're going to do this based on we're going to do this based on the x and q squared formulas that I'm sure you've seen like 10 times now, maybe over the last 2 weeks. So we're going to use q squared as the negative momentum transfer squared for momentum transfer squared. So that's incoming 4 vector for the electron minus outgoing 4 vector of the scattered electron squared. We could write this in lab quantities as well. That already indicates that there's 2 ways of calculating this q squared. We could either use the momentum vectors that we get from our tracking system, which is what we're going to do here, or you could use the energies that you get from the colorimeters. So there's going to be a redundance in how we measure q squared. Scattering angle could also come from either the colorimeters or from the tracking system. I'm going to ignore the y here, but then we're going to do x, which is q squared over s times y, or q squared over the dot product of p and q. So we're going to actually use this 4 vector approach and then do 4 vector dot products on what we determine. So we're going to scroll through this. Again, first we're going to load some of these Python packages. We're going to load the same file again. We're gonna load the reconstructed charged particles and get their momentum. Oops, these are all of the possible values we could get, but we're gonna load their momentum. So in this case, KP1, KP2, and KP3 are K prime with index mu, which is 1, 2, or 3. Those are going to be the 1, 2, and 3 components of K prime of the scattered electron momentum. Then we've got our particle code, and then we've got the mass of the particle, so we can get to the K0 component. So if we look at all of the masses for particles that have a particle data group code of 11, which are electrons, then we do see that those all seem to have a 0.511 MeV mass, or 0.000511 GeV mass. So we've got 3 components of our scattered electron momentum, of our scattered electron form momentum. We still need the 0th component of our scattered electron form momentum. That is going to be what we get from our momentum formula. So mass squared plus the 3 momentum squared, and then square root. So that gives us our 0th component. And it does this, by the way, for all scattered particles for every event in this data set, right? One of the things that Python is very good at is allowing you to write down these formulas, and really in the background it's doing this on 4,797 different tracks. You don't have to think about that, you don't have to write any loops, it just does it. So now we also need the incoming electron beam. The incoming electron beam is going exactly along the negative z direction. So it only has a K3 momentum component, which is negative 18. We're going to ignore the fact that this is probably, well, I guess, yeah, the momentum of the beam is 18 exactly, and the energy is going to be slightly larger than 18. And that's going to be our K0 component. So that's our incoming 4 vector. So now we can calculate our momentum transfer. For momentum transfer, all 4 components, Q0, Q1, Q2, Q3. That's the difference between the incoming electron for momentum and the outgoing electron for momentum. We can take the square, and in this case, I've not written this as an explicit for momentum dot product, but I've just written this as the net as the expanded components with the metric applied. So that gives us our Q squared, and we have our Q squared. Now we have a Q squared for every reconstructed charged particle track, some of which are going to be electrons, some of which are not electrons. Some of the electrons might not even be the scattered electron, right? So if we make a plot of this Q squared, we might have some questions about whether this is really the correct Q squared. Now you see there's some things that have a very high Q squared here. These are, I would venture that these are not going to be the right charged particles. These were probably not electrons that were the primary scattered electron. Now at this point we can't really identify that. This is the experimental problem in all particle colliders. We have to figure out what is the right electron to use here. Now, one thing we can do is just zoom in on this a little bit and look at the range from 0 to 100 GeV squared and Q squared, and just kind of take a look at that graph. And one of the things we actually see is that for this sample, for the simulation, which has a minimum Q squared of 10 GeV squared, we do indeed see that the events that we reconstruct mostly have a reconstructed Q square that is greater than 10 as well. So at least there's some connection to our inputs. Okay. So that's our Q squared. Now what about X? Well, we can determine X, And I don't think we have the formula. Oh, here is the formula for x. So it's q squared over 2 times p dot q, where p and q are again 4 vectors. Now we don't have the 4 vector p yet. We only have the 4 vector q. So we're going to have to calculate the 4 vector p, which is the incoming proton. So it's a 275 GeV proton beam, but it's a little bit rotated at a scatter at the crossing angle of 0.025 or minus 0.025. So this gives us, and it's rotated in the x and z plane. So that's why we give it this P1 and P3 component that are slightly different, and then we calculate our energy P0. So now P. Oh, is there? I see. Okay. So P dot Q is going to be this dot product. And then we can use this finally to calculate X. And now we've got a list of values for X. Again, everything in X is going to be for all charged particles, not just the electrons. So we're going to have to make sure we select only the electrons here when we plot X. Okay, so this is our plot for X. Anything obviously wrong about the plot for X? There's negative values. Yeah, we don't like negative values. There's values greater than 1. You know, this is the difference between theorists and experimentalists, right? Our X values, we get what we get. That doesn't necessarily satisfy the same constraints as what you expect from theory, because we have things that go in there that are not necessarily the right electrons, right? Resolution. And there's potentially issues with resolution. So we have to study all those things. So how would you study that? Well, one way to study it would be right now, for example, is to compare with the true information. Because in the truth information, in this MC particles record, we actually do know which electron was the DIS electron and which one was probably not the DIS electron, or at least we can compare whether what we get there is similar to this. Yep.
I guess something that I've always struggled with this concept is that what if your generator is wrong? Why are you really comparing to this truth? It's kind of a biased assumption.
Right? Generators can be wrong. So there's and generators can be wrong for a number of reasons. They can be wrong because of just bugs, or they can be wrong because, for example, they're assuming a certain PDF model, and that might not be accurate, or that might not be accurate enough. And as you can see, our events don't come with error bars, right? So so in that case, especially the PDF kind of issue, we would run with different PDF assumptions and see how much there's difference between the two, or between the 3, or between the 500 that are in LHA PDF.
Because like, what if, for instance, there is sense like not maybe
Well,
distance, but like
there's not going to be physics that is negative in X, because X is just in DIS as a quantity, it cannot be negative. You go to deuteron scattering, and X greater than 1 is certainly not disallowed anymore. But here for proton scattering, it can't, right?
Just in that general, like I knew it couldn't be negative in this instance, but like say like in another instance, in a general aspect, like why are we making these assumptions and limiting our space?
I'm going to direct you to Alexa for the kind of questions whether X can be negative, because I really don't. We would look at different event generators, right? And if there's a good model that someone comes up with, these are different things you should be looking at, then we would use that in an event generator and make sure that we can reconstruct those events. Yeah. Yeah.
So when we parameterize X as momentum fraction carried by parton, then X can be anything from minus infinity to plus infinity. Now, once we write down our factorized formulas, factorized formulas due to momentum conservation, for instance, for deep elastic scattering, we find out that the X, which we write in our theoretical formula, corresponds to X Bjorking, which is defined here. And for the X Bjorking that we define here, the bounds are from 0 to 1, provided that you do measurements on a single proton or neutron. So it's from 0 to 1. If you do it on nucleus, then X can be greater than 1. But I believe it cannot be negative, just due to kinematics.
So one of the things we can do here now, so this previous plot, the X was plotted between minus 0.5 and 1.5. We can sort of look at the range, you know, a typical range in which people look at X is in a logarithmic scale, right? You want to see how many 10 to the minus 1, 10 to the minus 2 events you have in here. And with the caveats that we're looking at, you know, sort of a poor electron finding strategy here, we can at least learn something about this. That, for example, there's going to be, let's say, this many events in this lower X bin, this many events in this intermediate X bin, and then we're not going to have a whole lot of events with an X that is going to be close to 1 in this 18 by 275 data set. Now, this isn't necessarily the best way to plot this in an X log scale because all of those bins are sort of different in size. So more frequently, you'll see this in X bins that are equal in size in a logarithmic scale. So here you would be able to say, for example, that in a logarithmic scale, most of our X is going to be, for this particular data set, for a minimum Q square of 10 GV squared, we're going to have mostly a sensitivity to 10 to the minus 2 to, well, between 10 to the minus 3 and 10 to the minus 1 in X. One thing that you will also often see is you'll see this represented in sort of this X and Q square diagram. And Abe showed a number of those earlier today, because it indicates where the EIC is having sensitivity. And so for this particular data set, it indicates that we are getting events in this X and Q square plot that are going to be primarily in this range, again, between 10 to the minus 3 and 10 to the minus 1 in X, and between, well, 10, of course, GV squared, because that's what we picked as the limit, the minimum limit in our generation of events. But then it goes up about maybe a decade in Q squared. And different data sets, of course, are going to, or different simulated data sets are going to be focusing on different areas of this diagram. There's a kinematically forbidden region up here. That's why this is cutting off that way. And one of the things you still have to do is, of course, weight that with the cross section that it corresponds with this entire data set. So now, next steps. All right, there's some next steps here. Now we could, of course, do this not just for 18 and 275. We could do this for different energies. See how that compares in this X and Q square diagram, where the different regions that each of those data sets are sampling. Now, of course, you don't need to run it through simulation for that. You can look at where in the detector those different data sets are really ending up. We could, of course, increase the statistical precision of this sample. That was one file out of 500 identical kinematic files. So we could increase the statistics pretty trivially here by a factor of 500, which would allow us to say more about this. Now, the other thing I should say is that anything that's easy, like calculating X and Q square like we did here, we already do in the simulation files and in the reconstruction. So there's actually in these files, there's a inclusive kinematics electron branch, which has X and Q square pre-calculated. So if we didn't make any mistakes, and we didn't make any mistakes in the central reconstruction code, you should find the same value there. That doesn't make this exercise irrelevant. It just makes it a good example for something that you can actually calculate. But ideally, anything that everyone is going to need, we want to make sure it's done centrally. So then there's no mistakes in it. So Last but not least, we're going to compare this x and q squared that we now calculated from our reconstructed charged particles with the true x and q squared that we get from our MC particles. That will allow us to look at resolution of x and q squared. Do we reconstruct our x and q squared with 20% experimental resolution? And this is really where the resolution of our tracking system is playing a role, or the reconstruction, resolution of the momentum in our tracking system, and the resolution and the angle that we reconstruct from the tracking system. So we're going to go through this again. It starts with this exact same thing, loading some packages, loading that file, same file, loading the reconstructed charged particle events. We're going to get our free momentum, determine our energy, and then incoming beam energy, calculate q squared, calculate the incoming proton momentum or momentum, calculate our dot product, calculate x. So we've done this now, essentially the same thing as in the last notebook, but now we're going to do this for the true information from the particles in the original event record. That's before there's any kind of effect from materials and from poor or imperfect reconstruction of the momentum. So this is very similar to what we did in the second workbook today. We're going to get the momentum from our original particles in X, Y, and Z. In this case, we know the energy. We can calculate our true q squared now using this different formula. We don't use the four momentum dot product formula for q here. We're just going to use the lab formula because, useful to show some different approach here. We can calculate our true y, we can calculate our s, and we can calculate our true x value. By the way, I'm plotting here the square root of the center of mass energy of the collision here, and the square root of s is 140 GeV in this 18 on 275 collision. So we've also seen that in a number of slides that the center of mass energy in EIC goes from 20 to 140. Well, this is the 140 in the 20 to 100. So finally, I'm going to select here only those particles that have a generator status that's equal to 1 and that are electrons. So now I can use this selection criteria to pick only the x values and q squared values for scattered electrons. So let's compare what we got for our reconstructed x and our true x. These should be 1-to-1 identical in a perfect world where we don't have any detector effects, where everything's perfect. Well, we don't do so well here. This one doesn't seem so bad. Maybe this could also be better. This one doesn't seem so bad. Here, let me start from the back. This doesn't agree very well. This seems to agree pretty well. This seems to agree pretty well. This one, no, there's no one to compare with it. We can compare, and we can already see that clearly we're not doing something that's completely silly, right? We get an x and a q squared that agrees pretty well. X at least. A q squared, same thing. Agrees. Maybe not so well. Agrees, and agrees. So for q squared, we seem to be doing pretty well. X maybe not as well. Again, same reason for why we get sometimes big differences. Maybe we just picked the wrong electron. Maybe maybe these particles were in a part of the detector where we don't have good momentum reconstruction. Those are all the experimental effects we have to think about. Now, to select a better electron, what we often need to do is figure out this, electron finder. And I'm going to do a very simple electron finder here. And I forget what it was here. We're going to use the electron with the highest q squared. This is not necessarily a good electron finder, but
Where one minus cos theta in the formula to show.
It's, yeah, I don't know why I have plus, why I have one minus here. Yeah, should it be minus?
I think in the formula that you showed before, it was one minus cos. I tried to calculate it quickly. It looks like one minus.
Yeah, you're right. There's a minus here. This is the angle in this formula is the angle over which the electron scattered. Because the electron came in from
Okay.
the 180 degrees, the scattering angle for the electron is 180 degrees minus theta, and that's why we use a plus here. So yeah, but yeah, good catch. So we're gonna now calculate the ratio of the measured to the true Q square. And just to make sure we have a single value for both the true and the reconstructed record, we're going to use this argument that we pick the largest, the maximum value of the Q square. So we have one electron that we're using per event. Otherwise, there might be some event that has maybe 2 electrons. So that gives us our ratio of Q squared. What would you say? I don't think we're doing too bad there. We're within, this is 5% deviation on one side, 5% deviation on the other side. Well, we're well within that. I would say we're probably within 2% of the actual Q square. So these are, of course, important things to study in simulations, is to figure out whether we can reconstruct X and Q squared correctly. And we can plot this again. How did I plot this? Oh, right. You can plot this as a correlation plot. So true or reconstructed versus true. So or reconstructed or measured Q squared versus our true Q squared is actually agreeing with what we have here. We can do the same thing for X. Make the same kind of plot. Yeah, as already seen earlier, for X, this becomes a little bit more difficult. Where this is 50% off, this is 50% off. So there's of course a peak here, but it's not so great. If we look at this in a 2-dimensional histogram correlation analysis, you see again that, well, you hardly see it probably, but there's a lot more off diagonal bins that are filled here, which would be, let's say this bin here, which has some events in it. It means that our true Q square was 2 times 10 to the minus 2, but we reconstructed it at 4 times 10 to the minus 3. So we were quite a bit off. Now that brings me to the end here. What will we do here that we can do better? Well, the thing that currently people are working on in the collaboration is figuring out better electron finding algorithms. We're using different ways of reconstructing X and Q squared. We don't just have to rely on the electron. It's DIS. We've got pions. We've got hadronic final states. We don't just have to use the information from the charged particle reconstruction. From the tracking, we can use the energy from the colorimeters. We can use all of that at the same time. We have an over-defined system. There's different other methods that use various, I didn't even put the double angle method here. There's different ways in which we can calculate this X and Q squared. And then there's even machine learning ways that take all of the different approaches to measuring X and Q squared and then calculate an X and Q squared based on that. Now, in any case, we're always going to end up with these kind of plots where there is a correlation matrix and it has off-diagonal elements. And we're always going to have to correct for that. And that is what we call unfolding. I guess that is what is solved to some extent by unfolding, because anything we measure versus X and Q squared will have to be corrected for the fact that we might not actually be measuring the right X or the right Q squared. And so That's the other thing that comes out of this is these off-diagonal elements, we can construct some matrix that we then can use to correct quantities that we measure versus x and q squared. Now, of course, you can take that to all of the other variables as well, y and so on. So I hope that gives you an idea of what's involved from start, to finish, from event generator to analysis and then interpretation with unfolding. That's it.
Never thank him properly. It's the second time I believe you teach this school. First time was online. It was a very real experience for everybody, including students. A lot of students participated, and to me at least, it's just amazing to be in the same room and be in person. It's a Herculean task, of course. A lot of people work on making sure that those tutorials are given. I believe tutorials actually are given also on Zoom. Periodically, right?
Yeah, these ones, we haven't actually done this one in the collaboration. So you all get something that even the people in the Epic collaboration have not seen before.
We have some GitHub page with all of this.
So these are in this Python analysis bootcamp. So you could, launch this on Binder, and it's going to start it in a Python in a Jupyter notebook, or you can start it in Jupyter Lab, or just different ways in which you can just do it all interactively. Well, connection refused. Okay, well, not today then. That should be no surprise given my success with technology.
They will be uploaded also in GitHub scripts, Python script. Yeah, the link.
So this, I didn't add the link to this Python analysis bootcamp to the lecture on the first day, but all of the other material is linked to the lecture materials on the first day.
First day.
Yeah.
Okay, thank you.
Yeah, the only thing that I haven't uploaded is my little piece for my own notes. Everything else is on GitHub.
This concludes our tutorials for ESC software. Thank you, Wouter. Third time, we are back at 7:30 for our discussions as usual. Normal Wednesday discussions. Are they on YouTube channel?
I don't think. I'm sure it's something like 10 sites. 10 yeah, like it's gone now, but it's still weird when I'm trying my detector.